So thank you, everybody, and welcome back to another day of Math 365. And so, yeah, I'll just try to keep track with my memory, and hopefully I won't skip too many details. Not working with notes today, but we've been looking at these so-called Fourier series in general. So we've been looking at L2 of some interval from A to B, the space of all square integrable functions defined on A to B. We noticed this was a vector space. It has an inner product. Given thusly. And there's some technical things going on here. Basically, if you're an L2 function, then this inner product is well defined. If you're not an L2 function, then it might not be well defined. So it is important that we're using this space of functions and not something else. That inner product gives rise to a norm, which gives rise to a distance function. We talked about that last time. Now, what we do is we then say, suppose that we have like an orthogonal set of functions, or even an orthonormal set of functions. Some authors call it an orthonormal system. So F1, F2, all the way up to Fn. Orthonormal being that Fn, Fm is equal to 0 unless n is equal to m, and then it's equal to 1. And we've seen an example of the orthonormal system with the sign nx, divided by L like L over 2. And so suppose you've got something like that, then you can create what you might call the, given a function f in L2, you can form what we call a Fourier series for the function. It's a tilde. It just means that this is the Fourier series associated to function f. You want to kind of get away from the idea that every function is always equal to its Fourier series. In certain instances, it will be. In other instances, it won't be. Same way that every smooth function has a Taylor polynomial, and yet, every smooth function has a Taylor series, and yet not every Taylor series is equal to the original smooth function. Your textbook author actually does make this mistake using like equal sign, but I think it's better to, at the beginning, just say they're associated to each other. They're not necessarily equal. Whether or not this is equal to that depends on which orthonormal system you pick. And we have found out that the constants Cn are just given by inner product of f with Fn. We've seen examples of this. And Cn are called the Fourier coefficients. This is called the Fourier series associated to f. And I want to do a little bit of linear algebra, I think. So this Fourier series the question that we kind of ask is, does this series converge? Does it converge to the original function f? And in what sense? Is it pointwise? Is it like uniform? Is it in the mean square sense or the L2 sense? So this is the limit. This capital N goes to infinity of the sequence of partial sums Sn, where Sn once again is just the sum of the first n terms of the function. And going back to linear algebra, so if you say define subspace S to be the linear span of F1 to Fn, meaning just linear combinations. Then from linear algebra, Sn is equal to the projection of F onto subspace S. Is that familiar to you? So if you take some vector space V, you take some subspace S, you've got some vector F, which in this case is a function, and then you take the projection of F onto S. It'll be Sn. And then you've got this error function determined by Sn plus En equals F. Remember, we already defined this little quantity En, which was like mean squared error. It was like F minus Sn, but then the L2 norm of that. So take the absolute value of this, square it, integrate it from A to B. And just so as not to confuse them, I'll put a little hat over this. So this E sub n is just F minus Sn. So the relationship between the mean square error and the linear algebra error there is just that this one is nothing but the norm of that vector, using the L2 norm, which is the appropriate norm to use on our vector space. So if you had linear algebra at Simon's Rock, then you should have studied this idea where you take the span of a collection of vectors, that's the set of all linear combinations of that vector, and a set of all linear combinations of the spanning set. And if you want to do something like take the projection onto a subspace, the formula is actually kind of involved if the vectors are just independent, but if the vectors happen to be orthonormal, then the formula is quite simple, and that's what's called the projection. And the fundamental thing that kind of makes all this stuff work is that, so of course Sn is inside this subspace S, it's in that span, and certainly the error is orthogonal. Is orthogonal to Sn. So if you take the inner product of these two things, you'll get 0. Okay. Any questions on that setup? Now what I want to show you is something that you already know from linear algebra. So when you take the projection of a vector onto a subspace, that projection is going to be the vector inside the subspace that's closest to F. So like you could have any other vector W inside the subspace, and you could look at the distance from, so you could pick like any other vector W inside the subspace, and you could consider the distance from F to that vector W. And the projection is the vector that minimizes that distance. So it's always going to be true that the distance from F to Sn is less than or equal to the distance from F to W. So this is kind of like a theorem which says for any vector inside the subspace, then it'll be true that the distance from F to this Fourier polynomial is less than or equal to the distance from F to that vector. So in your book, they're just going to say it like maybe take W equal to something like that. And they'll actually plug it in and work out the details. And it takes a considerable number of lines to do. Of course, if you're working with distances, this is equivalent to saying that distances squared satisfy the same inequality. So it's easier to work with this setup because you no longer have the square root. And of course, the norm that I'm referring to is the L2 norm. So that means that means what? So it means integrate the square of the absolute value of this from A to B. So my point to you, and just to like really drive it home, I'll even write that down, right? So what you're saying is that this inequality. Where W has this form, the F sub n are part of an orthonormal system. F is an L2 function from A to B. And I guess my point to you is that from linear algebra, you already know this to be true. So like in some sense, you don't need to redo the argument. But I'll redo it anyway because we're kind of talking in a new context, and why not argue in that new context and see how it works with this particular norm. So I want to do a proof of this. So I want to look at, I'll start with the right hand side. And I'll just drop writing L2 every time, but I'm talking about the L2 norm on this vector space of L2 functions. And so I want to do the mathematician's add and subtraction trick. So I want to look at, because I want to relate these two things together. So how can I do that? I want to add and subtract that error vector. So I want to do F minus E sub n plus E sub n minus W squared. And let's just play around and see what happens. So F minus E sub n is equal to Sn. It's by definition. This is the error vector. So F minus E sub n is equal to Sn. So this is like Sn minus W plus E sub n. And Sn and W, they live in the same subspace, right? So their difference is inside the subspace S. But the other thing that I'll point out is that kind of by definition, this error vector is orthogonal to subspace S. but by the way it's constructed, it's orthogonal to each basis vector Fn, and therefore orthogonal to the subspace. And the reason why that's important is that this is true for any norm. If you have two vectors that are orthogonal, then it's going to be true that a plus b squared, norm squared, is equal to norm of a plus norm of b. This is the Pythagorean theorem. Pythagorean theorem is valid for any inner product and associated norm, not just for the dot product and Euclidean distances. I give this exercise on the second or third day of linear algebra, but the way that you can do it is just remember what this is. It's a plus b inner product with itself. Like, isn't that the definition of norm squared? And then you'll just notice by orthogonality the cross terms drop out and you're left with that. So this fact that the error is orthogonal to the subspace was fundamental in our discussion in linear algebra when we're talking about projection, when we're talking about like deriving the formula for least squares, so on and so forth. And of course, it's fundamental here too. This is really a linear algebra argument. It only depends on the fact that the L2 inner product really is an inner product giving you a norm, and therefore you can do all this. So I've got this term that's orthogonal to that term. So this is now equal to like Sn minus W squared plus En squared, which is like Sn minus W squared plus En is F minus Sn. What are the two things I'm trying to compare? I want F minus Sn, the error, and I want F minus W. And so here's F minus W, and here's F minus Sn. Here's a term that is extraneous, but notice that this term, of course, is bigger than or equal to 0 because it's a length squared. And therefore, this right-hand side is now bigger than or equal to F minus S sub n squared. And then now we're done. Now we're done. So the proof is just sort of a quick couple of equalities and inequalities, but the two tricks are using the add and subtraction trick so that you're able to compare yourself to the error in the first place, and then also using the Pythagorean theorem, using the definition of error to note the orthogonality. And if you compare this to the proof in your book, that there's a lot less writing here than what they have to go through. Just because we know linear algebra, so we can do the argument quickly. And this principle is telling you that the Fourier series is the only series that has a hope of converging to function f, because any other series has to be a bigger distance away from f than your best approximation. So in the same way that Taylor polynomials are the best approximation to a smooth function, Fourier partial series, Fourier polynomials, whatever you want to call them, are like the best approximation to f. Similar principle leads us to this inequality called, so we've seen this name before. It's called Bessel's inequality. And Bessel wanted to relate the Fourier coefficients to the function somehow. And so under the notational setup that we've already established, what Bessel's inequality says is that if you take the sum of the squares of the Fourier coefficients, it's always going to be less than or equal than the L2 norm squared of the function, where Cn has this definition and where Fn is an orthogonal system. And this is similar type of arguing. Let's try to prove it. I'm going to start by showing, I'm going to first try to show something simpler, just that if I take like the first n coefficients, then that'll be less than or equal to that quantity. And how can I do it? So just using, let's just start with normal squared, and I'll drop this subscript for now because just to save some writing. What can I do? Maybe I don't want to start with that. Maybe I want to take inner product of Sn with itself. Let's try this out and see what we get anyway. Let's try Sn with F. Sorry, yeah, I don't have my notes, so you'll see me just trying a few different things to see what's works. But you see more how I think instead of following a script. So let's try this and just see what happens and see what we can make of it. So first, by linearity. By linearity of the inner product. So you can pull out the constant and the sum. And Fn, inner product with F, by definition, this is Cn. So this is, so actually, yeah, what I wanted to do was start with this side of the equation. So first of all, like, does that make sense? And Is there a question? Okay. Why is this automatically less? So I need to figure out how to introduce the norm of f. And so let me try something like this. Let me try even something different. I mean, this is fine, it's true, but I don't see a relationship to f. So I want to get one. So now I'll take this inner product. And so here I'll get f dotted with itself. And here I'll get minus 2 times dot product of f with Sn. And here I'll get plus inner product of Fn with itself. And this, of course, is equal to f minus S sub n squared. And so what's this equal to? So it's like equal to norm of f squared minus 2 times f dot Sn. But I mean, so this inner product is symmetric. It doesn't matter whether you do Sn dot f or f inner product Sn. So this is minus 2 times this sum and then plus this sum. What's your question? Okay. Plus this sum. So this is going to be this dot product. Little n going from 1 to capital N. And what you can see happening, you bring out, using linearity twice, you bring out c squared. I mean, I should really use different indices. This is like ck, fk. Okay, it goes from 1 to n. I'll let you check out this calculation. So what happens is you get 0 unless n is equal to k. And in that case, Fn and Fn have inner product equal to 1, and you're left with like Cn squared. So it's really the same. So you end up with length of f squared minus the sum. N goes from 1 to capital N, Cn squared. And that's equal to this f minus Sn squared, which is now bigger than or equal to 0 because it's the length squared. And now you're done. Now you're done because you've shown that f, norm of f, is bigger than or equal. Well, you're almost done. You've shown that norm of f is, you've shown this. Just moving this to the other side of the inequality. You've shown that. But now you're in a situation where on the left-hand side of the inequality, you've got a reference to capital N, but on the left-hand side of the inequality, you do not. So you can simply do this other kind of like analyst's trick of just taking the limit. It's a great trick. If you have an inequality, then limits will, if you have an inequality with less than or equal, then limits will preserve that inequality. That's just the limit law from calculus. But this doesn't depend on n, so this is still norm of f squared. The limit n goes to infinity, excuse me, of some n goes to capital M. And now you're done, because by definition, that is the infinite series. So this is Bessel's inequality. You check the chat. Yeah. Yeah, I apologize, for doing mathematics in front of you. But maybe that's not bad to see. So the question is, wait, what? Can you be more specific? Oh, yeah, I mean, if I had my notes that I brought, then I wouldn't have had to think through it and figure it out. So that's a little less time efficient. Okay. I mean, there's lots of reasons why this inequality is kind of good. For now, I'm just showing it. And the other kind of interesting thing that we like to show is, well, it starts with this definition. So let's say you've got an orthonormal system, and say that orthonormal system is complete if the following holds. If the following holds. So if F is in L2 AB, and if the inner product of F with Fn is equal to 0 for all n, so the inner product, so if F is orthogonal to every vector in this system, then F is equal to 0. Why do you need a definition like this? So go back to our orthogonal system of sine n pi x over L. What if I just took one of these out? What if I just looked at the system sine pi x over L, then I skipped 2 pi x. I went straight to sine 3 pi x over L, and then sine 4 pi x over L, so on and so forth. I mean, this is still a countably infinite orthogonal collection of functions. So just from the definition, you don't have any way of knowing whether you skip something that's kind of important. So this is incomplete, because there is a function f. In this case, f is sine 2 pi x over L, such that f is orthogonal to everything in this list, but f is not 0, so that is incomplete. So this tells you why complete is a good word to associate to this, definition. It means you didn't miss anything. It means intuitively, it means the orthogonal complement of, the orthogonal complement of all the fn's is just the 0 vector. So I'll tell you some things that are it's possible to show. So if Fn is complete, and F is inside L2 of AB, then it will be true that F is equal to its Fourier series. But remember, when someone says, like, this is equal to a series, you always have to ask how. In what sense does the series converge? It's in convergence of norm, so it's in the L2 or mean square. Sense. So F being an L2 means that with respect to the norm that you have on L2 functions, that this series will converge to F. So maybe it won't converge at every single point, but it'll converge in the mean square sense. How do you prove something like this? So this isn't an analysis class, so I won't go over it in detail, but you just need one more definition, and then you can almost do this. You prove that the linear span of the FNs, so the collection of all finite linear combinations of, selected from the FNs, you prove that that is what we call a dense subset of the vector space. And then, using properties of being dense, like once you know that word, you can make an argument that this has to be true. And we'll learn later on, or at least we'll use the fact that sine n pi x over L for n equals 1, 2, 3, that is a complete orthogonal system. So for any L2 function on A to B, it will be true that F is equal to its Fourier series. So that'll be like a nice thing to have. Yeah. So Bill's pointing out that I misspoke. So you should include the cosines. You should include the cosines. And the cosines will go from, n goes from 0, 1, 2. Right. This one's complete for the vector space where like the endpoints were 0. But we'll learn that when you include the cosines, then it's a complete system. Thank you. So yeah, let's actually just kind of talk about that. We've done enough theory. There are some theorems I can say that give you conditions under which the Fourier series converges pointwise or uniformly, but I think we should kind of get into actually doing something. So let's try that. So there are lots of orthogonal systems that you can work with. The one we're interested in now that kind of came from our discussion of heat equation was the one with sines and cosines. So what you might call like a classical Fourier series is take the orthonormal system where you've got sine n pi x over L, you've got cosine n pi x over L. This one starts at 1, that one starts at 0. So in order to kind of fix that, it's common to do this. It's common to say something like A naught over 2 plus sum from n goes to 1 to infinity of an cosine n pi x over L plus b sub n sine n pi x over L. And so now this is like specializing to the following case where you've got interval AB. equals symmetric interval from L to L. And we'll figure out how to handle a non-symmetric interval later on. And so this will be a Fourier series with the orthogonal system given to you by like F1 equals constant A naught over 2, or like F1 equals 1, like F2 equals cosine pi x over L, F3 equals sine pi x over L, F4 equals cosine 2 pi x over L, like so on and so forth. So you can, the collection of the constant, the sines and the cosines constitute a single orthogonal system. You can index them with the natural numbers. And we want to kind of figure out like what are the coefficients. It's called the Fourier. Coefficients. And we kind of already did this for the sines. So if this were orthonormal, then your A sub n would just be inner product of f with cosine n pi x over L, right? But since these aren't exactly orthonormal, they're just orthogonal, you also have to scale by the length squared here. So you get cosine n pi x over L cosine pi x over L. This is something we worked out last time, right? So did we figure out that that was L over 2? I feel like we figured that out. Although last time we were going just from 0 to L. So maybe the constant's multiplied by 2. Because we could just figure it out. I'm not going to remember this, but I also don't want to figure it out. Woe is me, right? Does anybody have the formula at your fingertips? You can get it from this equation, and this one's just the inner product, that's right. And then it's just a question of what's this constant? I'll give you a minute to look it up. You have to help me help you. I feel like it's going to be 1 over L. I mean, so failing a student looking it up for me, I guess we'll have no choice but to kind of work it out and see what we get. So let's just do like cosine squared n pi x over L dx. So this is like 0 to L and twice. Not super interested in doing the integration by parts. Anyone want to save me? Yeah. Okay, well, actually, I changed my mind. I'm not going to do this for you. So you can do this for me. You can do this for me and verify it yourself. This is a very doable integral from your Calculus 2 class. And I'll give you an assignment over the weekend. I'll ask you to please take f of x equals x on -1, 1, and please calculate. This would be kind of like my last example, but ran short on time. So please calculate the Fourier series. So since f is an L2 system, and since this orthogonal system is complete, even though we didn't show it, but it is, it will be true that in fact f is equal to this expression with the coefficients, for an given by this formula, coefficients for bn given by the corresponding formula with sine n pi x over L. And you'll need to look up these scalars or just do the integration by parts and you'll find it. I think that formula is correct, but maybe I missed. Just from this formula, yeah. So when you do projection, when it's just orthogonal, not orthonormal, then you have to have like length v squared on the bottom. So I think it gives you 1 over L, but I'm not. But you can check. Yeah. That's the thing. Well, it's whatever goes here. It's the reciprocal of whatever goes here. So I guess it should be like L or something. Yeah. And then after doing that, just calculate those other coefficients and figure out the Fourier series for x. And this will give you a nice formula for f of x equals x, like as a series. And we'll look at maybe a couple pictures of like the different terms and showing the sine waves kind of, sines and cosines kind of converging to get to it. So thank you everybody for your time and attention. I apologize for the disruption for getting my notes, but that's okay. And thank you everybody. Have a great weekend. I'll see you today at 4 o'clock perhaps.